So, hello everyone. Myself, Gaurav Kumawat, coordinator of Isaac Bhopal Astronomy Club. And after the orientation session that we did last week, here we present the second talk of this semester. And today we have with us Mr. Aayush Verma from BS 2020 batch. And he will be giving a talk titled Marvels of Space Engineering. And we will be having the Q&A session at the end of the talk. You can keep posting your questions in the chat box. We'll take note of those questions. And if there is any urgent question.
So hi guys, my name is Aayush Verma. I'm from second year Engineering Sciences, Indian Institute of Sound. So let's continue. So we are going to talk about the launch vehicles. Launching a rocket into space is one of the humankind's greatest achievement. Although there come in different shapes and sizes, all the rockets are propelled by engines that produce thrust. A launch vehicle or a carrier rocket is a rocket-propelled vehicle used to carry a payload from Earth's surface to the space or into a Earth orbit. A launch system includes something which you can see in this figure. It includes launch pad, vehicle assembly, and fueling systems. This is a space shuttle, which you can see in this picture. And yeah, let's proceed. A rocket that is launched into space is made up of four major systems. Based on the function, the structural system makes up the frame that holds the rockets together and consists of the cylindrical part, the body, the nose, and the fins. The next is the propulsion system that takes up most of the space, including the rocket engine, diesel, the fuel which is used, and the oxidizers. The payload system depends on each and every mission and consists of the rocket, which is actually taken to the space. It could consist of a satellite, a human being, or anything which is yet to be taken to the space. So it depends on each and every mission. Lastly, this is the guidance system. Is made up of radars and the computer that provides the stability for the rocket and controls the maneuver during the flight. Yeah. So let's talk about the structural system of the rocket. Here I've shown three different launch vehicles, as you can see. And here is a person standing over here in comparison to a launch vehicle. As you can see, a launch vehicle can span up to 250 feet or even higher. And we would examine each of the parts of the launch vehicle. So this is the first stage of the rocket. This is the second stage, and this is a two-stage rocket. Respectively, this is a three-stage rocket, and this is the Ariane 5. As you can see, this is the schematic of the Ariane 5. We are going to talk about the staging of the rockets in the later slides. So yeah, so here you can see there is a thermal shield over here. This is a solid rocket motor, and to protect the main SSME from the solid rocket motor's heat, we have provided a thermal shield over here. And we have oxidizer tank. We have solid fuel tank, which consists of the rocket fuel, which we usually call it. And here is the inter tank, which differentiate between the oxidizer and the rocket motor fuel tank. So it is very important, as we all know, these tanks are pressurized to maintain the center of pressure of the rocket. In any flying object, the center of pressure is pretty important. Yeah. So this is a three-stage rocket, and you can see a specific part which is known as fairing. This fairing actually protects the spacecraft or the payload while taking off and while launching from the air drag. Yeah. So this is a schematic of Ariane 5, as I mentioned, and this is the actual rocket which was launched by the NASA. Yeah. And these are some of the launch vehicles of the ISRO. The first one is the Satellite Launch Vehicle, SLV-3. This is the Augmented Satellite Launch Vehicle, ASLV. This is a Polar Satellite Launch Vehicle, XL. We have very variations in PSLV. We could change the number of solid motors in this, and we can vary the payload capacity of PSLV. Similarly, goes for the GSLV, which stands for Geosynchronous Satellite Launch Vehicle, Mark II and Mark III. So the difference between Mark II and Mark III, as you can see, is the payload capacity. It has a payload of 2,200 kgs, and this has a payload of 4,000 kgs. Moving to the next slide, I guess I missed this one. The space agencies of the different other space agencies. So as you can see, we have many space agencies in the entire world, ISRO and NASA and SpaceX being the famous one. And these are some of the rockets which have been launched in the history of the world. So you can have a look at them. Then I will change to the next slide. So yeah, I guess it is not visible, the heading. Is it visible now?
It is visible.
Okay, okay? It is visible. So in earlier times, rocket stability was very important. So we used to have fins in the body. As I think I don't have a picture, but we used to have fins in the body. But what were the drawbacks of the fins is that they used to provide a lot of drag during the launch, increasing the fuel cost. So then we actually developed a system known as gimbal thrust system. So an important aspect of a rocket flight is the stability and the control of the rocket. And the rocket uses all type of aerodynamic forces to provide some measures of flight stability. In order to complete a successful mission, a full-scale rocket is designed with system for both stability and control. The guidance system usually includes sophisticated sensors and computers to detect the orientation, location, and the speed of the rocket. In a gimbal thrust system, the exhaust nozzle of the rocket can swivel from side to side. As you can see in this animation, this is a nozzle which I am talking about. It can swivel side to side. You can see it moving, right? It's a GIF.
Yes, we can see that.
Okay. So as the nozzle is moved, the direction of the thrust is changed relative to the center of gravity of the rocket. On the figure, as shown, there are three cases over here. In the normal case, the thrust is aligned with the center of gravity of the rocket, and it moves straight upwards. And in this figure on the left, as you can see, the thrust is now inclined at an angle of A, which is known as gimbal angle, towards the left. So what happens eventually is that when this angle is when the nozzle is moved towards the left, it produces a torque on the entire rocket towards the left, resulting in moving the rocket towards the left. And this is the same how we actually change the direction of the rocket too. And in the right figure, as you can see, we have moved the nozzle towards the right, and there is a thrust generated towards the right. Eventually, the force is generated in the rightward direction. Yeah. So this is the gimbal thrust effect, which provides stability to the modern rockets. That is why we don't have body fins right now in the modern rockets. So then we are going to talk about the most interesting part, which is the rocket engine. So basically, there are many types of rocket engines, but I've covered two of them. First is the solid rocket motors. They're much more better than like easier to maintain. And okay, let's talk about it. The key advantage of the solid rocket motor is that the fairly simple mechanism. There is no moving part involved unless there is a thrust vectoring control system is used. The propellant is typically stabilized and can be stored for years. It is very easy, and it is not like the other one is called as liquid propellant rocket engine. It is much more complex than this. It has fuels which are very low temperature, maintained at very low temperature. So these are much simpler to store for years. And a typical rocket motor consists of an igniter at the top, as you can see over here. Once the rocket is started, it cannot be turned off until it's burns itself out. Like it is like Diwali rocket, as you all know. It is like a big scale version of a Diwali rocket. If you once ignited, you cannot stop it in between. So the propellant used in this is actually called as grain. The nomenclature is the grain, and it is typically solid, and which consists of 85% of the total rocket motor's mass. The grain is mostly solid with burning surface built into it. By burning surface, I mean the shape in which it is built. So I will tell you why the shape is important. Yeah. So the exterior to the grain is some sort of thermal. Then I was explaining you about about how the grain is filled inside the tank. So there are different methods which we can fill shapes into it. So few of them are these: end burn, grain, internal burning, tube, and slots. So the difference between all of them is the time it has the maximum thrust. So if you look at the graph, you can see that the external burning rod has the maximum thrust initially. So like in some missions, we do need a very heavy lift off. So we use these type of motors, solid motors, so that we can have a maximum thrust at the starting. And similarly, opposite to that, internal burning tubes, we have the maximum thrust at the last, which have its own uses. And there are many other types which could keep it neutral, and other ways too. And this is the composition of the grain in the solid motor boosters. Right. And as I mentioned in the previous slide, there is a casing which is used to keep the grain. So these casings can be reused and can be filled with the grain again, the propellant again, and used in another rocket. So this actually reduces the cost of the rocket making. So yeah, so we all know that SpaceX is trying to do that, which could actually help in reducing the cost of each and every flight, which we rocket flight. So it would be a very good example to career to pursue in the future. So the next type of engine is a liquid propellant rocket engine. A normal liquid rocket engine has a combustion chamber, a nozzle, two fuel tanks, and pumping from it is a simple liquid rocket engine. That propellant is fed into the combustion chamber by static pressure from the tank. The oxidizer and the oxidizer and the fuel are stored in the liquid state instead of their native gaseous state. Here, the propellant are fed into the combustion chamber by static pressure in the tank. High pressure gases generated by the evaporation of a liquid propellant is used to force a fuel and an oxidizer into the combustion chamber of the rocket. Here it is ignited to produce. So I would like to continue. Very sorry about the disturbance. So all the engines basically works on the Newton's third law of motion. If you push the gases downwards at a very high pressure, then the rocket will be lifted up in the air towards the space. Yeah. So this was all about the liquid propellant engine. Now we would consider a very important aspect of an engine, which is cooling the engine. So in the figure, this is a zoomed part of an SSME. SSME is the space shuttle main engine. So here you can see that the pipes are running down the nozzle, connecting the channel through the rings around the belly part of the nozzle. So the pipes flow liquid hydrogen fuel into these rings, which are known as the cooling channels. The cold liquid propellant around the nozzle is to keep it cool for two reasons. The simplest one of the reason is the structural integrity. The temperature and the pressure inside the SSME nozzle are quite high, placing the material in a very extreme environment. Keeping the nozzle walls cool help maintain the material strength. The other reason is that the temperature of the nozzle walls as constant as possible. So the first reason was that there is no material yet, like there could be, but the material used is not that hard to hold the structural integrity of the rocket at such a high temperature. And the other is to keep the rocket at minimum lowest temperature possible, so that there are no heat spots generated on the nozzle. If the heat spots are generated, they may de-direction the gases output which is coming out from the nozzle, and could decrease the efficiency of the nozzle. And this type of cooling, in which we rotate the hydrogen fuel around the nozzle in a circular rings, it is also known as regenerative cooling. And there is one more type of cooling which is also known as radiation cooling, in which we use a material which has a very high melting point, so that when the rocket is running, it could reach a constant point where the temperature gets constant, and it could radiate all the heat out into the space. That is why it is called radiation cooling. Okay, so I guess it is all about the cooling of the engine. Now we would shift to all we studied right now was the four systems. First one was the structural, second was the propulsion, third was the payload, and the fourth was the guidance. Payload and guidance I did not talk about because they are actually depends on the each and every mission. Payload could be any satellite, and guidance systems are used to locate the location of the satellite. So in order to launch into space, all these four systems of the rocket should work together to overcome the force of the gravity. The launch begins when the propulsion system generates. The launch begins when the propulsion system generates a massive amount of thrust. This thrust is the force produced by burning fuel as the gases escape through the engine. Once the rocket generates enough thrust to which is equivalent to its own weights, we call that a liftoff. It is one of the most exciting and the most important part during a flight, and uh, during this part, during the power ascent, the weight of the rocket continuously changes as fuel consists of a lot of weight of the rocket. So as the fuel is burned, the weight of the rocket also changes, and we need to do the calculations rightly to actually achieve the right speed of the rocket so that it could enter the Earth's orbit. Uh, as a result, most of the space-bound use a technology called staging to reduce the dead weight and increase the efficiency. So I would talk about the third stage, which is called staging. There are actually two types of staging. First is called serial staging, and the second is called parallel staging. So all the rocket used to generate thrust by a propulsion system to overcome the weight of the rocket. For a full-size satellite launcher, the weight of the payload is only a small portion of the liftoff weight. Most of the weight of the rocket is weight of the propellant, and as the propellant are burned off during the power ascent, a large proportion of the weight of the vehicle becomes nearly empty, and the structure is still on the vehicle. So in order to lighten the weight of the vehicle to achieve the orbital velocity, most launchers disregard a portion of the vehicle in a process called staging. So first is the serial staging, and what happens in a serial staging is that the rocket is stacked one upon each other. The whole rocket is divided into two or three parts, and then it is stacked one upon the other. And as each of the fuel on each of the parts gets exhausted, it is eventually disregarded and thrown into the oceans or anywhere. Like earlier, it would not be collected back, but nowadays we reuse them, so we can collect it back from the ocean. So this type of staging was actually used in the Saturn V rocket. Saturn V rocket was a three-stage rocket, and but at that time the reuse technology was not yet discovered, so we could not get the parts of the rocket back. And the second part is called the parallel staging. As shown in the figure, we have small rockets strapped onto the main rocket. So these strap-on rockets are usually solid rocket motors. So once they all get exhausted, they are just disregarded into the oceans. And the difference between these two is that all the motors in each of the stack is ignited together, but these strap-ons are exhaust earlier and they are just disregarded, and the main SSME still burns and takes the satellite up to the desired orbit. And nowadays we usually have a combination of both of these two type of stacking. So yeah, let's move. Yeah, so the last stage is the cutoff. As the rocket continues into the orbit, its sophisticated guidance system maintains balance and steers to keep the rocket flight trajectory on the track. As the correct altitude and speed is reached, the upper stage engine cuts off, completing the rocket's journey from Earth space into the orbit. Yeah. So we have completed the first part of our talk. So now I would like to ask you a question which is really interesting. I hope you're all there and listening. So could a sufficiently athletic astronaut could throw a ball back to Earth from the International Space Station? Like if a person, there is an astronaut in the space station, could he throw a actual football or any ball from the space station back to Earth?
I guess not.
Answer that.
Yeah, you can unmute and answer.
No.
Like, I guess the velocity of the ball would be equal to that of the satellite. So it would continue in the circular path of the satellite.
Uh,
If the astronaut throws it opposite to the orbital direction, and if he throws hard enough, then it may go to the Earth.
It may
Yeah.
burn also. If if suppose we have thrown it and it will burn from atmosphere.
Yeah.
Right. That is a good observation. But yeah, almost all of them were right. I guess, yeah, you all knew about this question. But yeah, mostly what people think is that we have zero gravity in space. So if we throw anything from the space station, it is going to land up directly on Earth. But it doesn't happen in that way. So actually what is going to happen, I will tell. If you can see in this diagram, first the ball will, the astronaut will be able to see the ball going down. But as we know, as it deorbits, the ball is going to get much more faster, and it is actually going to go faster than the space station itself. So the astronaut will see the ball going ahead of it and going down, but eventually the ball will stop going down, and then it will eventually rise again. And about half the orbit later, the ball will be actually at once again back with the same height altitude from the Earth as the space station. And this is the most fun part. It will actually rise again, rise above the space station, and rise, as you can see over here. The ball will actually rise over the space station, and then and if you hit it, if you throw the ball exactly rightly, then it will again hit the space station back after one full revolution. Sorry. So what really happened is that when we threw the ball, the astronaut threw the ball, it got a vector in this direction, vector velocity in this direction. So the path of the ball changed from circular to elliptical. So this has a very little eccentricity, but it is yet elliptical. So the ball will again revolve around the Earth in an elliptical part and hit back the space station right after one revolution. And as you can see, it is not a simple addition, it is a vector addition. So the change, even if the astronaut throws the ball at around 100 meter per second, the change in the total velocity would be around 0.7 meter per second. As we all know that the space station revolves around the Earth at a very, very high speed of about 7.5 kilometers per second. So it would not make much of a difference to throw a ball at any speed from that. If you do the calculations right, it is about 4 times the speed of the space station. So which is not humanly possible. So yeah, the answer is no.
Bhaiya,
Yes.
for this ellipse, Earth is focus by
Yes,
Kepler.
of course. Yeah. The Earth will be the focus, right?
Yeah, I think it would not hit the astronaut again, because the Earth is not a perfect sphere, so the gravity is not uniform for every.
Oh, that's a really good observation, I would say. Yeah, we are going to talk about it again. But yeah, it will actually hit the astronaut back. I will tell you that also.
But it won't change anything for the first orbit. Like after 100 years, it won't hit.
After 100, sorry, I could not get you.
Immediately, the orbit won't change that much. It will hit in the first orbit, but after so many orbits, the ball will eventually go far away.
I don't understand, like, on what basis are you saying this? Like, is there any logic why the ball would go away?
And also there can be atmospheric braking, that many satellites experience it due to solar panel and deployment of solar panel. The atmosphere.
I totally get you, but we are talking about a hypothetical condition over here, so we don't need to talk about solar radiation and all. But yeah, you are right.
Solar panel, the satellite, the atmosphere breaks satellite, means reduces the speed of satellite.
Right. You all are right. We'll talk about it later too. Yeah. Thanks for speaking up. But yeah. So as you all were saying that why it would not hit the ball would not hit the astronaut back. We will talk about it in this part. So we are going to will discuss 4 different types of orbit. First is the LEO, low Earth orbit. Second is the MEO, medium Earth orbit, and the third is the GEO, which is geosynchronous Earth orbit. And we are going to also talk about 2 special type of orbits. First one is going to be sun synchronous, and the second one is going to be Molniya, or you can call it Minion Orbit. Many of them call it. So the first, sun synchronous has a very high inclination, and it also has a the eccentricity of the sun synchronous is pretty close to 0. But in Minion orbits, it is highly eccentric, and it is in the medium Earth orbit. Okay. So let's review some of the key terms. I guess you all know these terms. These are all 12th nomenclatures. Orbital altitude is the height of the orbit above the surface of the Earth. Right, you all know this. And this one is the semi-major axis. I guess you have studied it in 12th. The second term, the average distance between the apogee and the perigee is known as semi-major axis. If you want to simply state that, then the distance between the apogee and perigee is the major axis, and it is a half is known as a semi-major axis, right? And what is apogee? Apogee is the farther distance of an ellipse, and perigee is the closest distance with respect to this foci where there is Earth. Perigee is the closest what do you call it, edge of the ellipse, right? And the period is the obviously the revolution time taken by any satellite for one revolution around the planet. And according to Kepler's third law, the semi-major axis and the time period, the relation between that is the Kepler's third law. So there is one more. Sorry, I missed this one, I guess. Orbital inclination. It is the inclination from the equatorial plane. We'll study about this one too in the further slides. So yeah, this one states the Kepler's third law. The lower the orbital altitude, the lower is the energy, and the higher the overall altitude, the greater is the energy. Right? We all know that. So there is one more interesting question related to this in the further slides too. So stay tuned. So the next is the lower Earth orbit. So the lower Earth orbit has an altitude varying from 100 kilometers to 2000 kilometers, and it has an orbital speed of around 7.84 to 6.9 kilometers per second. It has a time period ranging from 86 to 127 minutes. So yeah, depending on the altitude, it will have the orbital velocity and the orbital altitude. Altitude. Yeah. So the next one is the geosynchronous, which we all know, the most famous one. Unlike LEO, it has an exact altitude above the Earth, which is 35,862 kilometers from the surface of the Earth. I've mentioned that, right? And 3 kilometers is the 3 kilometers per second is the orbital velocity, and 24 hours is the time period. So that is why it is most important, because it has a time period of 24 hours. So what is the uniqueness of this 24 hours? That it is going to be in sync with the rotation of the Earth. So at this satellites always moves in the space at an exact longitude. So if you're standing at a longitude, then you will be able to see the satellite throughout the day at the same exact location, right? So it is why it is a very important orbit, geosynchronous Earth orbit, GEO. And this is a view of the geosynchronous orbit from the space. Like you could see the entire Earth. So if you plot it on a paper, then it will look like this. And in between the LEO and the GEO is the MEO. Like it also has varying altitudes. So a GEO with corresponding orbit, it has a velocity, orbital velocity of varying altitude. Oh, sorry, not velocity. It has a time period of about 12 hours. Like there is a special altitude at which is known as semi-synchronous orbit. It has a time period of about 12 hours, and it is very useful too. Like you could revolve 2 satellites in combination so that it could work as a geosynchronous satellite. If you are able to understand, like if you are revolving 2 satellites in medium Earth orbit, then it would eventually be useful so that we can cover the half Earth. If you are talking about the northern hemisphere, then it could be very useful. 2 satellites combination would be very useful. So this is also a pretty important orbit. Yeah. So here comes a pretty interesting part, right? So there is something known as J2 effect. So as you all mentioned during that question, that Earth is little bulged and in the middle. So actually it is 21 kilometers extra than the radius of the Earth at the equator is 21 kilometers extra than the radius to the poles. So this actually creates a effect known as J2 effect. So if I would state that what is the space shape of the Earth, then it is not spherical, it is oblated, right? It is a little bulged from the center equator side. So so we need to ask ourselves the same some questions like why does it affects the orbit? So the answer is that the force based on this oblated Earth is called as J2 perturbations. But where does the term J2 comes from? The term J2 comes from an infinite mathematical series that describes the perturbational effect of the oblation of the gravity on the satellites. The coefficient of each of these terms in the series is described as J of k, where we have three type of terms, which are J2, J3, and J4. They are known as zonal coefficients. So among these three, J2 is one of the most powerful one. It is almost 1,000 times powerful than J2, J3, and J4. So we only take into account J2. Okay. So it is a little bit difficult for you guys or new, but yeah, try to understand it. It has a very useful use in the sun synchronous orbit. So yeah, so the J2 perturbation will move the RAN over time at a constant speed depending on the orbital size, shape, and inclination. Using this property of J2 perturbation, we can manipulate our orbit so that the RAN changes at a speed of about 360 degrees per year, keeping the orbit in the same orientation with the sun. This is called a sun synchronous orbit. So this effect happens between 95 to 105 degree. However, yeah. So in this picture, if you could see, this is a sun synchronous orbit versus a non-sun synchronous orbit. So if we don't consider the J2 effect, then this red path is eventually projected. Like it is a mathematical concept, so we can calculate the mathematics behind that and just predict the path. So if we don't consider the J2 effect, this red projectile is eventually figured out, but it was wrong. So we have to consider the bulge of the Earth too. So if we put the satellite in the right orbit at an exact altitude, then the J2 effect comes into picture, and we can set the RAN of the satellite in such a way that it is around 360 degree per year. So as you can see over here, the satellite is always in the syn with the sun. So it provides a lot of advantages for observing the sun. So in these type of satellites, remote sensors are used, and which could actually report to the Earth in the right time. Like they revolve around the Earth at an exact time. If you could see, the sun sets at the right time and the sun rises at the right time, right? It is always fixed. We can predict it. And similarly with these satellites, with the RAN effect, exactly with 360 degree per year, we could predict the rise and the set time of these satellites, and it is always constant in syn with the sun. So yeah, and you can see in this image too, the bulge effect, the RAN effect over here, J2. So yeah, as I explained, in the sun synchronous one, the exact RAN J2 effect is exactly kept at 360 degree per year, so that it could be in the syn with the sun. And here is an image of some of the satellites that LAND Landsat is one of the satellite, which is a sun synchronous satellite, and it has an altitude of around 709 kilometers. So you can just Google it out. It would be really interesting to know about them. Right. So the last orbit which we are going to talk about is the Minion Orbit. So if we look into technical specification of this kind of satellite orbit, it has an eccentricity of 0.7 and an inclination of about 63.4 degrees from the equator, obviously. These satellites are actually used for internet needs and observing the solar views. Polar areas. Like they're highly eccentric, and by highly eccentric, I mean they have a very small perigee and a very high apogee. So it is very, very useful. I will tell you why. Because if you look into this diagram, it has a distribution of the time period of the satellite. So as you can see, it spends a very, very less time in the southern hemisphere, and almost the entire time period of the satellite goes into the northern. The satellite is above the northern hemisphere. So in this diagram, you could actually see why this is very useful for human needs. This is the ground tracking monitor. Oops, sorry. Yeah. So this is a ground track report of a Minal satellite. So as you can see, it spends most of its time in the northern hemisphere and over the continents which we actually live. So it is like it wastes less time in the oceans and river oceans, where we don't need any where we don't have the satellite use, and it is actually used in combinations like medium Earth orbits. Like 2 of the Minal satellite could actually cover the northern hemisphere almost 24 hours, because most of the time is spent on the northern hemisphere. And here is an example of 2 Minal satellites, and which, as you can see, that they have a perigee of around 600 to 700 kilometers and an apogee of about 40,000 kilometers. So yeah, it is very, very useful satellite, and it has an inclination of 3.4 degrees. The inclination is pretty important in this case. So yeah, this is a very, very fun question. As you said in the first question that why the bulge takes place. No, this is not about bulge. Yeah, very sorry about that. So yeah, there are 2 orientations of the satellite shown over here. So which one do you think could attain a high speed and could actually go faster, and which one do you think is much slower than the other?
Left one, high drag orientation.
Yeah, high drag is faster or slower?
Faster.
Oh yeah, you know the answer. Very nice. So
Faster.
yeah, others? Anyone could guess? Take a guess. Yeah.
Yeah.
Yes,
If
yes.
it is facing more drag, it shouldn't be slower. Yes, slower. Yes.
Yes, exactly. That's what I wanted. But you guys are too smart to give the right answer. Yeah. So what happens in real life, that if it is at a high drag orientation, it should be slower, and at a lower drag orientation, it should be faster, right? It is much more lower drag orientation is much more streamlined than the higher drag orientation. But what happens in real life is that when this satellite, when it is oriented in high drag, these are known as Dove satellites. They're very small satellites. They don't have their own thrust or combustion engine, but they do have a system which can change their orientation. So what happens that when these satellites are launched, they're launched in like groups, 5 to 6 satellites together at the same altitude, and they are to be distributed all around the Earth at an equal space. So if they don't have thrusters, then what they're going to do, they're going to change the orientations. So when it enters into the high drag orientation, it slows down for some seconds, but then what happens, it gets into a lower orbit. And as I mentioned in the earlier slides, that when the satellite gets into a lower orbit, it actually becomes more faster, because low altitude, high speed, and low energy, right? And high altitude, lesser the speed and high energy. Sorry about that. So yeah, so as it enters into the low altitude, it gets faster than the low drag orientation, and eventually it goes much more faster, and there is a then we could achieve what we wanted, that they could be equally distributed around the Earth. So yeah, and it was actually like this. If you don't guess this part of the talk, then it is like it is okay, because there was one mission, Gemini 4, I guess. In that mission, the real life astronauts were actually given this task to reach the space center, and they were accelerating. So what we usually do is that what is our actual like normal ideology is that if you want to run towards someone, then we're going to reach that person, right? But in space, if you accelerate, then you're actually going into a higher orbit and you're slowing down. If you actually put on your brakes and deaccelerate, then you are actually going into a lower orbit and eventually getting faster. So Yeah, so those two astronauts were like most brilliant astronauts of the United States at that time, but still they were not able to figure that out. So yeah, this is pretty interesting and important. So let's move further. So as I mentioned in the abstract, that we are going to talk about the Mars a rover 2, which went on Mars. It is known as a Perseverance Rover. It was actually launched on 30th July 2020 from the Florida launching station. Just a second, I will just drink some water. Sorry. Yeah. So launching the next generation of the Mars exploration vehicle on the red planet. Yeah. So launching the next generation vehicle on the red planet, it consisted of two parts: the Ingenuity Helicopter and the Perseverance Rover. On 18th February 2021, almost 1 year from today, the two vehicles landed safely on the Martian surface after a 7-month long journey to the red planet. And as a fact, only 40% of the mission dispatched to the Mars have succeeded yet, after facing a brutal and a complex landing sequence, which is also known as sky crane landing sequence. The Perseverance rover is one of the largest and the heaviest rover ever launched to Mars by the NASA, or we call it JPL, NASA's Jet Propulsion Laboratory. And yeah, so talking about this slide only. Yeah, so there are also a bunch of great new software updates, like the algorithm that determines when the parachute should be open. So earlier in previous rovers, after the hypersonic entry, like that is the most important difficult part for any sort of vehicle to rover to pass through. The hypersonic entry of about 21,450 kilometers per hour is drained off. Earlier the parachutes were released at a speed of 1450 kilometers per hour, but in this special Perseverance rover, the accuracy of the landing was improved, and it would only deploy the parachutes once it has reached the optimum landing trajectory. So to do that, the sky crane method was developed, and it was modified too. It would just scan the surface of the Mars in which it was going to land, compare those images with the earlier images which it already had, and then choose a best site which has the less obstructions, and land on that place. So it could improve the efficiency of the working of the rover on the Mars to a very high extent, and we have seen that it works very well. That if you choose the right site, then your entire journey on the Mars becomes very easy. So the next was the radio thermal generator. So thermoelectric generator, like this is the powerhouse. So it powers all the devices on the rover. So the Curiosity rover and the Perseverance rover both had the same thermoelectric generator. It is also known as RTG, thermoelectric radioisotopic thermoelectric generator. And the RTG works by transforming the heat generated by the radioisotopes natural decay into the electricity. It generates energy via a basic principle known as Seebeck effect. So I guess you have all heard about the Seebeck effect, but I will explain it a little bit. The carrier charges, both the electrons and the electron holes, migrate from hot to cold. The Seebeck effect allows us to generate an electric current through a heat differential. Yeah, it works on this principle that whenever there is a difference between the heat, difference between the temperature, it generates electricity from that. It is a very complex process. So the decay of the radioactive element produces heat. The heat source from the Perseverance rover RTG is a 4.8 kilogram plutonium dioxide. It is a radioactive substance, mostly creates alpha waves, which is crucial because this type of radiation converts into heat in the most efficient way and in a very small space. So the plutonium dioxide has a half-life of around 87 years, which is like much more than the rover's life. So it was very good option as a fuel. And it is also non-radioactive, which is kind of exciting, or you could say new to us. Like it is non-radioactive, so in case of any sort of failure during the launch, like if the rocket burns off in the atmosphere, it won't pollute the environment. Radioactive substance could. So going to the next one, MOXIE. So the full form of the MOXIE is Mars Oxygen In Situ Resource Utilization Experiment. So it is actually a small prototype of the actual instrument which is going to be launched to Mars in case we are going to establish a human life on Mars. So MOXIE is a revolutionary oxygen generator that will put to test as a part of any human future missions to Mars. You might be wondering how this is different from the oxygen production on board to the International Space Station. So there is a definite finite amount of oxygen available. Why are we testing a new technology on Mars, which we have, but we have already have a technology on space station, which is worked and which is proven, right? So yeah, the space station does not recycle oxygen in a significant way. Like in space station, what we have is that we in the production of hydrogen and oxygen, oxygen is produced through the electrolysis of water. So this results in the production of hydrogen and oxygen, and water and methane are formed when the hydrogen reacts with the carbon dioxide, and the methane in then is simply expelled into the space while the water is reintroduced into the system. We lose 2 hydrogen atoms for each and every oxygen molecule we make. Thus, the International Space Station needs to be resupplied with the water regularly. But water is a pretty heavy commodity to be transported to the Mars, right? So we need to figure out a new way to actually produce oxygen on Mars. So what this MOXIE does is it uses solid oxide electrolysis to break the abundant carbon dioxide in the Martian atmosphere into oxygen and carbon monoxide. Right. So for any future missions to Mars, oxygen is going to be critical. We all know that. So NASA is planning to launch a full-scale model of MOXIE, which could produce oxygen to about 2 kgs every hour, and it is going to be launched with an empty vessel or an empty rocket where the oxygen can be stored, and this oxygen will be the vital element which is going to be used in the future missions. So actually I turned the slide. It was all about MOXIE. Then in the next slide, this is a sample coring drill. Like we all know that we are actually searching life on Mars, right? So this sample coring sample drilling experiment is like it drills holes in the Mars, collect the samples, and then analyzes the samples. So it has many instruments in that. It has radioactive scanners, and eventually we are looking for life somewhere. If we are able to find life in Mars, so it has many scanners and all. So that, and it is going to store the soil sample into this tube, which is known as SAM. So, and what we are planning to do is that we are going to leave this SAM on the surface of the Mars, and then in the future missions we are going to pick them up and launch it into space, and then the orbital, which is actually revolving around the Mars, will be able to collect it and send it back to Earth. So it would be a great raise the hand. Oh yes, Gaurav.
How many slides are remaining?
Just one, last.
Because since we already passed 1 hour, so yeah, I can.
Realize it. Yeah, sorry about that. But the last is
actually we passed 1 hour, but it is so interesting that we can also take more time.
Oh, thank you, Tariq. Thank you very much for that compliment. Yeah. So the last one is the Ingenuity Helicopter. So this is one of the most exciting feature of that mission. So if the mission is successful, that humanity will be proven to control a controlled flight on the space. So we know that the density of the Mars is about 1% of the density of the Earth. So it is very, very difficult to actually fly something on the Mars. So what we have taken some measures for that, it doesn't have a Taylor rotor. So what we are doing is we are going to rotate the propellers in a way, in a counter what do you call that? Sorry about it. In the counteract, so that there is no need of a tail rotor, and they could fly in a much more stable and controlled way. And as I told, the density is only the 1%. So the RPM should be very, very high. It should be around 2,400 RPM, which is much 5 times faster than any RC helicopter which is on the which is on the Earth. So the blades and the blades also must be composed of a very high strength carbon material, so that it could actually withstand that centrifugal force which comes with that. And even the blades have a very, as you can see over here, has a very significant greater angle of attack, and which is much more than the standard blades, so that it could actually throw much more air towards the ground than usually what you see in RC helicopters, right? So, and even this helicopter doesn't have it's going to be detached from the Ingenuity Helicopter, Perseverance Rover, sorry. So it needs to have its own power source. So unlike if you heard of the Dragonfly mission to the Titan, it is not like that. It doesn't has its own RTG, but it is going to have some lithium ion batteries and solar panels. Those solar panels will be able to charge those battery and give this drone a small, not a drone, a helicopter, a small power boost, which so it could have a flight of about 90 seconds in the atmosphere of the Mars. So yeah, I hope you really enjoyed the talk. I am Aayush, as I mentioned, second year student of Engineering Science Department. You can contact me on these numbers, and this is my email ID, Insta ID. You can contact me on WhatsApp too. So yeah, please shoot with the questions.
Yeah, so thank you so much for the wonderful talk, Aayush. These are some questions that were in the chat. First, I'd like to address those, then you guys can unmute yourselves or ask in the chat. So the first question comes from Swapnil Anand. Does space rockets and missiles are having same structures?
Like who has a question can ask themselves if it is okay, if they are present. Okay.
Are you there? I'll just put it in the chat for you to see.
Yeah. Okay. Thanks a lot for that.
No.
Does space rocket and the missiles have same structure? So yeah, what happens in missiles is that they use solid rocket motors. As I mentioned, they're much easier to keep, right? You're not going to use the missiles every day, right? They're not something which needs to be used or addressed every day. So they have rocket motor boosters. So yeah, you are right about that. That some of the, like, as I mentioned, PSLV, if you remember, all the rockets also have solid rocket boosters. So yeah, missiles do have solid rocket boosters, but they don't have liquid propellant rocket engines. So yeah, missiles and rockets are somewhat similar too. So what is center of pressure? Yeah, that's a good question. So in flying objects, center of pressure is important, because if you had like there is center of gravity, right? So center of gravity is something where all the gravity acts. We can assume it be a small object, right? At that point. So even at the center of pressure, all the drag and all the forces which are acting because of thermodynamic property of that rocket act on that point. So it is a little below the center of gravity. If you can Google it up, you will be able to see images. But in flying objects, thermodynamics is pretty important. So all the drag forces and all the forces, like we have 2-3 forces acting on the rocket in the atmosphere. First is the thrust, which is able to lift it up, and the second is the drag. So these all forces actually add or subtract, and they act at a point which is known as the center of pressure. Yeah, thanks for the question. What are red and green circles? I guess this question is from this slide.
The J2 effect one slide.
Right. That effect is, it is very difficult to figure it out. But yeah, so these red circles are actually the trajectory if the J2 effect is not considered. Okay, so as I mentioned, J2 effect is because of the bulge in the Earth equator. So if it is not considered, then you can see that the orientation of the satellite will remain constant, right? But it doesn't happen that way. You have to consider the J2 effect, and if we set it at the right altitude, it is going to be sun synchronous and eventually have a path in the green circle. So these green circles events represent a sun synchronous orbit. So as you can see, they are in syn with the sun. So if you can just Google now, you will see animations, but how it moves along with the axis of the sun. So it is like always facing towards the sun, right? It is always facing towards the sun, the green circle. So it is very useful for sun observations. Sun is pretty important for us. So we actually have orbits to observe sun. And there are many satellites too on that path, as you can see in this image. Yeah. So
Yes, the next question comes from CS Aditya. Is Molniya orbit same as GTO?
okay, just a second. I guess I missed it. Yeah. Yeah. That's the question.
Hello, Aayush.
Yeah. Yes.
Okay, one of the student asked that will you like share the slides? So if this is possible.
Yeah, sure. Why not?
I asked, Bhaiya.
Yeah.
Yes, what's your name, bro?
I forgot.
Sir, Raj Soni.
Oh,
Yeah.
very nice to meet you. Yes, I will definitely share the slides with you. Even I have given you my contact number. You can contact me. I will share the slides personally too. Or we will mail everyone as the coordinator wishes.
The slides will be like sent to the IBAC follower group and the whenever group. So if you are there, you will get. Also, we can we can also share it via the website.
Okay, IBAC WhatsApp group.
Yes.
If you are there on the.
Yeah, this question now. What Molniya orbit same as GTO? What is GTO? Sorry.
GTO is geosynchronous transfer orbit.
Oh, geo. You mean geosynchronous. Oh, no. Molniya orbit is much more complex than the geosynchronous. Yeah. So this is the slide. As you can see, geosynchronous is it has almost eccentricity equal to 0. They're almost circular orbits around the Earth. But Molniya is like, it has a very high eccentricity and even a very high inclination. So it actually takes place, like there are many terms I'm not familiar with that much, and you guys will get confused if I explain them to them. There is something known as argument of Perigee. So at some argument of Perigee, the orbit gets logged. The perigee of this orbit gets logged over here. So it won't change. So this type of orbits are specially like exact altitude only. They are launched, like they're very difficult to achieve too. So if they're launched at an exact altitude and exact orbital velocity, they achieve this type of orbits. So as you can see it, I guess this answers the question. It spends most of the time in the northern hemisphere. Unlike the geostationary, it revolves around the Earth in a symmetric way at a single longitude. So yeah, it is different. Yeah.
Right. So the next question is from Viru Kumar Singh. Please explain why is the high drag orientation faster? So this was after your explanation of the drag thing, but it was answered in the chat. Do you still want it to be elaborated, Viru?
Yeah, please say that. If you
I have
still not
understood.
got it. Yeah.
Okay, works. We can move on to the second question. The sixth question. Prajwal Sanskar, is there catalyst? He is referring to the reaction of hydrogen, carbon dioxide converts to methane and water.
Yeah, this reaction takes place. Thanks, Ranjan, for the question. Yeah, so this reaction takes place in the International Space Station for generating the oxygen. I guess you have mentioned it. Yeah, right. This reaction takes place in the International Space Station. So yeah, of course, there is going to be a catalyst. It is much difficult process. I've just simplified it and told it to you. You can just Google it up. The electrolysis of water. It is much more difficult to actually perform that.
Yeah.
Thanks for the question, Prajwal.
Right. Anyone else would like to ask anything?
Someone has raised his hand, I guess. Yeah.
Hello, am I audible?
Yes.
Yeah.
Yes. First of all, the slides were too good and great talk. Thanks for that. And
thank you very much.
The thing I wanted to ask is like, how can I look up further into this? Actually, I'm very interested in rocket science also, along with astronomy. So I follow channels like Garib Scientist and Everyday Astronaut, but when they go into the technical part, I start to lose them in the half of the video, and find it really hard to understand them. Like, so how can I look them up? Like, can you suggest any sources or any other things like for the basics?
Right. For the basics, I will share you a book which I referred to. Like this talk, I have been working on for more than 10 to 15 days. Like every day, I used to read something. I used to figure that out. Due to effect and all, as I told, it is very, very difficult to understand. It has a lot of mathematics in them, and they are pretty interesting if you want to. As I told the story, like the real life astronauts which were in the space at that time were not able to figure out how to reach something in front of them in the space, right? So it is difficult. So yeah, so if you are interested in this, it is a very very interesting field to move in, as we all are excited to go into ISRO and all. I will share a book with you. It is completely based on rocket science, how a rocket is designed. If you talk about rockets, you can speak on and on and on for like 2 to 3 days, still it won't get over. So if you want to actually read, then you can read that book. If you want sources, then yeah, YouTube is the best source, man. Like if you type let's say Minion Orbit, as I mentioned, so you can just type it, you will see a lot of videos. Grab something or the other from a video. Like if you want to actually gain the knowledge and not any sort of certificate and all, you can just Google it up. You can read all the websites. You will grab something each and every website. So that is a good way of figuring it out. And there are some programs of the ISRO too. If you could Google, there is, I forgot its name. There is a program of ISRO where it is like NPTEL course only. You can just I'll share the link on the IBAC Forever group, so you can do that. And yeah, one more thing, very interesting thing, as you have asked. I've written an article on the Perseverance Rover, so you can read that up too. I'll just share the link of that article in the chat box. Yeah. This is our IBAC website. We post amazing articles on this. Not my only article. There are many awesome people in IBAC core committee who are actually working very, very hard for contents to create. So even if you read all these articles, I'm pretty sure you are going to improve your knowledge. Like from each an article, you are going to learn something new. And one day you will be writing an article from our website for our club too. You could join the club.
Yes, yeah. Yes, sure.
You can just read the article.
Can you please share that astronaut video also?
Oh, sorry, astronaut video, which one?
You were talking about 2 astronauts, like they were given a task.
Oh, yeah, actually I don't remember, but I remember roughly that story.
Okay, I'll try to search it up. Fine.
Yeah, sure. Search Gemini 4 mission.
Okay, sure.
Yeah, you will find out. Yeah. Any other questions?
Any more questions? Anyone?
There are like too many chats. I have not read the chats. Like, is there
no,
anything?
the questions in the chats were addressed, I guess. Right. Any other questions from you guys?
Excuse me, Bhaiya.
Right.
Yes, Bhaiya.
Yes.
Can a BSMS student get a job in space industry?
Oh yes, of course. If you do physics major, you can get a job anywhere. Like physics is something. Yeah. If you want to do PhD, then it is like your choice. But yeah, many of the physics major people get a very good job in these space agencies. Like it is all about physics, right? Not only engineers. Engineers are also required to work in harmony. So yeah, you can get a good job in ISRO after doing physics major.
Actually, I read an article yesterday about that our new chairman of ISRO visited ISER Kolkata, where he gave a speech about that the data we collect by our space missions in ISRO, ultimately we should use it for the improvement of science, the knowledge of science, to make intellectual property, to increase the knowledge pool. So we need more scientists we need quality scientists in our space agency.
Right.
Like that.
Right. Yeah, absolutely. Like ISER is famous for research college, right? All of these things I mentioned, they're like combination of engineers and scientists, right? The new technology, the new experiment, which is like if a scientist engineer designs how to model this MOXIE, and the science will be based discovered by the scientist, right? So yeah, it is all about working in harmony. You can do anything, engineering or physics majors. If you have interest in it, then like it is not bounded, right? Earlier, it was like there is no boundary between chemistry and physics, right? Even thermodynamics in chemistry matches up with the physics thermodynamics, right? So there is no boundary in sciences. You can study anything if you have interest. Don't need to shift your branches and all. Don't need to worry about that too much. You're going to have pretty awesome courses in ISER. So do
Actually, the
study your
clubs in
academic stuff.
ISER are also very helpful because clubs have many, very much diverse topics to talk about. Like
Right.
some days before, I attended the IBAC, IBAC orientation, in which Gaurav Bhaiya introduced about website and articles. So
Right.
that, I mean, was very informative. Thanks for all this.
Thank you very much. Gaurav, a compliment for you.
Yeah, thank you very much for that. We really appreciate your enthusiasm.
Right. So there is another question from Prajwal in the chat. Why is staging required?
Yeah, I guess I explained this like during the entire talk. Sorry if I stop the presentation. I will just explain it verbally. So what happens, like we have stages. Sorry about that. Yeah, so like we have stages in the rocket. So the payload is at the top, right? So if we are able to divide the rocket into smaller parts, then we are what we are doing is we are increasing the efficiency. Fuel is very expensive and it is heavier. So if we are like if the fuel burns, then that container is empty. It is going to just add up to the weight of the body. And sometimes we need a very large velocity. Like if we are going to Mars, then we are going to actually escape the velocity of escape the gravitational force of the Earth, right? So we need a very high velocity to launch. So achieving that with the empty tanks is pretty heavy. It is pretty not inefficient. So we stage out all those empty vessels in which were only used for the lift off and up to a very like usually it goes for 130 seconds. Where it could reach a very good height, and then you can stage out the solid rocket boosters, and then the main SSME is also in serial staging. The SSME is also staged out, discarded. So yeah, staging is pretty good and efficient way to save the fuel. I would say. Yeah, thanks for the question.
Any more questions, anyone? Right. So Satya, I guess there are a lot, but I can't recall any. You can search upon LinkedIn, I guess. I've seen quite a lot of them. So Aayush, do you know of any? Is there any?
Can you repeat this question? I could not figure out what.
No worries. Is there any alumni of ISERB in any space agency or any private space agency?
Ooh. I have no idea. Gaurav Bhaiya knows. Yeah. He's the coordinator.
This is Harshal Vasnik. He is in the there is this astrobiology sector that's growing within ISRO recently. So he actually worked there for some time. He was in 2015 batch, I think. So yeah, he's passed out now. He's currently pursuing his PhD somewhere in Ireland. But for a brief time, he was actually working on the project there, and he used to even come for IBAC and gave talks on astrobiology at this time. He was a bio major, so yeah, ISRO he used to be there, part of it.
So yeah, I would like to introduce Kevin Bhaiya. He is one of the smartest person you would ever meet, or like if you talk to him, even if you talk to him, your knowledge is going to go up. You don't need to read books, just talk to him. Message him, like trouble him on WhatsApp.
He is a cool YouTuber also.
Yeah, you can follow him on YouTube. But apart from YouTube, he's one of the most smart guy I've ever met. The most knowledgeable guy.
Okay, thank you. That's good. Yeah. So other than that, yeah, I also don't know if anyone else who has been part of any space organization, but yeah, he was pretty famous when he was around on campus. He used to wear a ISRO ka jacket and.
Right, so this is IBAC for you guys. Not only we host astronomy session, but we also give life advice. Right.
Yeah.
So
With that
okay.
too.
Any more questions? I guess we are falling short on time, so you can maybe send it in the IBAC Forever group or IBAC Whenever group if you are part of any. Right. So thank you so much everyone for your time, and thank you Aayush for such an informative talk. And again, sorry for the interruptions, guys. Sir,
Yeah.
internet is not.
Really sorry, guys. Really sorry. It was not in my hand. The
Right.
internets were
Yes,
fluctuating.
sir needs to fix that too. Okay, we'd like to improve our flow of talks from the next time, hopefully, and do follow us on our social media handles. I guess, right? Can anyone post the link of our social media handles?
Oh yeah, I will do that.
Right. Okay, and thank you so
You
much
can
for
find it in the description of the IBAC Forever group. All those
Forever.
links. Yeah.
Yeah. Right. Thank you so much for your enthusiasm, guys. Okay. Right.
See you
would like
soon
to
in the next talk. Thank you very much for joining.